Good afternoon. Yeah, good. Welcome to One-Click Statistical Modeling. My name is Tyler, and I'm a software engineer with Tableau. How many of you have used Tableau to answer a question? Oh, I'm sure it's way more than that. Come on, throw your hands up. Let's go. Yeah, that's why you're here, right? How many people have used statistics in Tableau to answer a question? So fewer of you. That's okay. So for those of you who have used statistics to answer a question in Tableau, you may have noticed that those statistics are really good at answering certain types of questions. So our goal today will be to see what types of questions are good, or the features in the analytics pane are good at answering, and so that you can take those with you and answer some questions that you have. First, a little bit about me. Before I came to Tableau, I wanted to be a math teacher. I got about 5 weeks into my student teaching, and you know what I found out? Teaching was not for me. What was for me was quantitative reasoning. So I went back to UW, I got my master's in applied math, and ended up at Tableau, where I get to engage in quantitative reasoning every day. I still love the act of teaching, and I really believe that anybody can answer questions like a data scientist. So TC Week is perfect for me because I get to be a teacher for about a week, and then I get to go back to doing linear algebra, or whatever it is we're doing. On our agenda today, we will talk briefly about the analytics pane, confidence intervals, trend lines, forecasting, clustering, and hopefully we'll have some time at the end for questions. If we run out of time at the end, I can hang out outside and answer questions for however long. So, yeah. Do you guys see the microphones in that middle row there? If you have a question, it would probably be better to ask it into the microphones so that other people can hear your question, and so also I can hear your question. So, how do we do it? Well, pretty much everyone has answered a question using Tableau, so you know that you need to connect to the data and create a visualization. We will use the analytics pane to perform our analysis, and then we'll interpret the results. So I put an asterisk next to interpret results, because this is really the meat of what we're doing. Using the analytics pane is really easy. It just requires a single click and a drag. But it's what we do with those results that will answer our questions and where we might have to do a little bit more work. So where's the analytics pane? It's right there in the upper left-hand corner. We click on it and zoom in a little bit. You can see that there are 3 sections. We will spend most of our time using the tools in the model section, as promised. In addition to being into quantitative reasoning, I'm also really into fitness. Do we have any fitness enthusiasts in the crowd? Good, a few of you? CrossFitters? Just one, okay, that's all right. So, for the fitness enthusiasts out there, you may have wondered, as I did, can I run a mile faster than the average second grader? So, I sought to answer this question using 1 mile run time data from my nephew's elementary school. Let's take a look. So this data set is 1 mile run times collected from my nephew's elementary school. They recently did a 1 mile time trial, and I was there to collect some data. I'm going to drag out converted time and place that on rows. That is the total number of seconds for each run. Now that's not particularly useful. That's the total number of seconds spent running by all the kids at the same time. Not really that great. So I'm going to split that up by grade. And again, this is the total running time for each of the grades. Let's break it down by first name. Okay, there are our run times. I have a sample of children from an elementary school in Seattle. It would be erroneous to use this sample to infer about the population of second graders around the world, so let's narrow it down a little bit. I would like to know if I can run a mile faster than the average second grader in Seattle. From the analytics pane, we're going to select average with 95% CI. It's right there. And then I'm going to do that per cell so that we get an average and confidence interval for each grade. That gray line through the middle is the average for my sample. The shaded region is the confidence interval. The definition of a confidence interval is that for 95% of samples, the interval will contain the population average. Now, I only have the one sample, so for this particular sample, there is a 95% chance that my intervals contain the population average. So to answer my question, I just need to make sure to run a mile just below where this line is, which I'm honestly not sure that I can do. So before we start trying to think about how quickly I run a mile, may draw your attention to something else. Do we notice how the bands are wider in the 1st and the 6th grade than everywhere else? Why do we think that is? I'm hearing sample size? Yeah. We have fewer data points. In order for our confidence interval to capture the population average 95% of the time, we either need a lot of data so that we can narrow down where that is, or we have to cast a really wide net. Any questions so far? Okay. Let's move on. The definition of confidence intervals is something that is often misremembered or misunderstood. So I put it up here on a slide. The definition of a confidence interval is that for 95% of samples, the confidence interval will contain the population average. For a particular sample, as often we only have one, there is a 95% chance that the confidence interval contains the population average. There is one implicit assumption that I made, however. Does anybody know what that is? I'm hearing sample size. Okay, normal distribution. So not quite. The assumption that I made was that my sample, in particular my nephew's elementary school, is representative of the population that I'm inferring about. In particular, I assumed that my nephew's elementary school is representative of all 2nd graders in Seattle. Is that necessarily true? Not necessarily. So this is kind of where we have to rely on our knowledge of the data. So maybe I can really only run a mile faster than the average 2nd grader in North Seattle, for example. So it's important to note that when using confidence intervals, that you know what your sample is representative of, so that you know what population you're inferring about. Confidence intervals are good at answering questions like, what does my sample of mile runtimes tell me about the average 2nd grader in Seattle? Or, is the average 2nd grader in Seattle likely to run a faster mile than me? Confidence intervals work very well for a single measure. How many people have at least 2 measures in a data source? Oh, I'm sure it's way more than that. Okay, yeah, good. You may ask, what is the relationship between those 2 measures? We can try to answer that question using trend lines. Before we look at some data, though, we need a little bit of terminology. The null hypothesis. In the context of trend lines, the null hypothesis is the hypothesis that there is no relationship between the 2 variables. Visually, it looks just like this. It's a flat line through the average of the data. So keep this picture in mind. Residuals. Residuals are the difference between my dependent variable value and the fitted values. In this image here, the residuals are just those little black line segments. Okay, let's look at some data. I have a data set here with a number of measures about a CEO and their compensation. So how do each of my variables relate to CEO compensation? I'm going to place compensation on rows. That's my dependent variable, because we'd like to know how compensation depends on the other variables. Now, the other variables I'm curious about are age, place that on columns, experience, also on columns, and profits on columns as well. So that's not very interesting. Let's break that down by individual companies. Okay, there's our data. Is there a relationship between each one of these variables and compensation. From the analytics pane, we're going to drag out the trendline object, and you can see right away it asks me to choose a model type. Theoretically, I don't know how each of these variables would relate to compensation, so I'm just going to pick linear. Linear is always a good first guess, and we'll talk a little bit later about why that is. But for now, Tableau gave me some trend lines. Tableau's trend lines uses an analysis method called ordinary least squares. In order for our ordinary least squares estimates, that is, the values on the line, and their confidence bands, which we'll talk about later, to be valid, we need to satisfy a number of assumptions. The assumptions have a mathematical statement, but I boil it down to a set of questions that we'll need to answer yes to before we can believe that our estimates make sense. The first set of questions we've kind of already answered. Do I suspect that there is a relationship between the two variables? And what do I suspect that relationship is? So does everybody remember the picture of the null hypothesis? Does the null hypothesis look like it's a good hypothesis for these data, at least compared to the lines that are already there? No, not really. Remember, the null hypothesis is that flat line, right? So a line having a slope indicates that there may be a relationship there. Now, this can be a little bit misleading because you notice how the axes are all different? So thankfully, we don't need to rely on just our eyes for this. We have a metric that helps us figure it out. So I'm going to zoom in here. All right, that number at the very bottom, that's the p-value. That is the significance. The p-value, in the context of the entire trend model, is the probability that we would see the variation we see given the null hypothesis. So for this particular trend line, there is a 13% chance that we would see the variation we see given the null hypothesis, which is pretty good, right? Well, it's okay. Because if we come over here to experience, we can see that the p-value is 2%. And if we come over here to profits, we can see the p-value is even smaller than that. So I do suspect that there is a relationship between each one of these variables and compensation, but in the interest of time, let's just pick the one that appears most interesting, so that would be this one. Oh, and the second question there, what do I suspect the relationship is? I already suspected it to be linear because it's a good first guess if I don't already know. Okay, so first set of questions answered. Let's focus on just profit and compensation for the next one. So in order for our model estimates to be valid, we also have to make sure our residuals look good. Do the residuals have a mean of 0? And do they appear unrelated to the independent variable? Okay, so before we can answer this question, we need to compute the residuals. Does everybody remember what the residuals were? I see some nods. Okay. The difference between the dependent variable value and my fitted values. The dependent variable is right here, that's compensation. So all I need to do is compute the fitted values, and then I can just subtract the two. So, oh, and of course, the fitted values are given by the equation of the line at the very top of the tooltip. Something times profits plus some constant. So I'm going to create a calculated field on profits. Let's call this fitted values. Let me zoom this in. I think I can do that. Can you guys see that okay? Yeah? All right. So I'm just going to hover over the line and type in that equation. 0.933774 times profits plus, there you go, 993.5. It's always a little scary typing in front of people, but I like to live on the edge. Okay, so those are our fitted values, and then we'll just compute the residuals from there, which are the difference between the dependent variable, so that would be compensation. Let's call this residuals, minus the fitted values. A brief caveat for computing residuals in this way. This calculation is static, which means it will not necessarily the equation that you put in there will not update with changes in the viz. that trend line that we put on there was computed at the level of detail of the viz that we have. And thus, the equation only really makes sense at the level of detail of the viz at which we computed the trend line. So when we're using our residual and fitted values calcs, we have to be sure that we're at the level of detail of the trend line for those to make sense. Okay, so how do I analyze my residuals? Well, there's something in there about the independent variable, so that'll tip me off that I should plot the residuals against the independent variable. Independent variable, remember, was profits. Let's place residuals on rows. And I want this at the level of detail of the trend line, so let's place company on detail. And that's what my residuals look like. Do they have mean of 0? Well, I can use the analytics pane. I'm dragging out the average line this time. That's this one right there. And I'll place that on residuals here. Yep, they sure do. This is something that we'll check visually. Do the residuals appear unrelated to the independent variable? Yeah, they sure do to me. It looks like the null hypothesis would work great for this data, right? And indeed, these are an example of residuals for a valid model. This is something like what you want your residuals to look like. Okay, so our model estimates are valid, but what does our model tell us about data that we don't have? So for that, we will have to use the confidence bands. Confidence bands are very similar in concept to confidence intervals in that they give you a range in which the true model is likely to lie. So, should we add the confidence bands? Well, we need to answer a couple of questions first. It's question 3. Are the residuals unlikely to be correlated with one another? So it might actually help to be looking at the residuals while we do this. So let's make that residuals viz again. Let's place residuals on rows, profits on columns, and company on detail. Okay, that's better. Are the residuals unlikely to be correlated with one another? Well, we can't really answer this question just by looking at them. We have to use our knowledge of the data. So do I believe that the difference between the fitted values and each CEO's compensation to be related? In other words, is the variation that we're seeing in our data, or in each data point, related to the variation in each other data point? These numbers come from companies that are all different sizes, all different industries. So it is very unlikely that the variation between two is related. So we can say, yes, the residuals are unlikely to be correlated with one another. Now that last question, does the spread of the residuals look roughly the same with changes in the independent variable? So that's why we have the residuals back up here again. Does their spread look like it changes very much? Not really. So, I mean, there's some clustering here, but we don't really care about the clustering. We just care about the spread, right? Which is, they seem to span this whole area, maybe except for this point here. And indeed, this is an example of residuals for which the spread does not really change with the independent variable. So we can trust our confidence bands. Let's go ahead and add them. So here's that trend line that we had before, exactly the same viz. I just wanted to highlight different questions at the bottom. And so then I'm just going to right-click on the trend line, choose Edit Trend Lines, and I'm going to check the box to show confidence bands. And just like with the confidence intervals, when we have more data, we can really narrow down where the true model is going to be. But then when we have less data or no data, we have to cast a wider net in order to capture the true model. So that was easy. Everything worked on the first try. What happens if you guess the model type wrong? You choose linear, and it's the wrong type. Let's take a look at the windmill data set. So if you've done the online training, you probably have seen the windmill data set. So let's suppose I own a windmill farm, and I would like to know how much power output I can expect based on data on wind speed? Now, that's actually a pretty complex question to ask, but let's just figure out what the relationship between wind speed and power output is for any given windmill. So I'm going to place wind speed on columns. That's my independent variable, because power output is going to depend on wind speed, not the other way around. Power output on rows, and I want this at the level of detail of individual windmills. Does it look like there's a relationship there? Yeah, so I certainly suspect that there's a relationship there, and I suspect that relationship is linear, because I honestly don't know. Let's say I forget the theoretical physics for a moment. So from the analytics pane, drag out trend line and choose linear. Okay, it looks pretty good. Is this trend line significant? Yep. There's a very small probability. Let me zoom in on that for you. There's a very small probability that we would see the variation we see given the null hypothesis. So it's certainly worth doing the residual analysis on to see if our model estimates are valid, which is good because I already did it. This is what the residuals look like. Do they have mean of 0? Well, let's drag out that average line, place it on residuals. Yep, they sure do. But do the residuals appear unrelated to the independent variable? That's not quite so clear, right? It looks like they're kind of grouped up together, then they all kind of fall off, and then go up and come down again. So these are an example of residuals for a model that has been misspecified. I chose linear, but the true model is actually something else. Okay, well, if that didn't work, let's try something new. So here's the same viz, the windmills again, but I'm just going to drag out a trend line. So linear didn't work. Let's try logarithmic. Does that look like it's a good fit for the data? No. So you can save yourself some work. If visually your line doesn't go through the data at all, don't even waste your time on the residuals. It has been specified. Okay, well, there's only a few models left. Let's try them all. Exponential? Nope. How about polynomial? Oh, hey, it worked. Cool. Okay, well, the p-value is good. R squared is really good. Oh, I didn't really talk about R squared very much. Does everybody, how many people have heard of R squared? All of you? Okay, I better mention it. So, the R squared value is the coefficient of determination. You can think of it as explained variance. So the model that we fitted here explains 98% of the variance that we see. When a model has a really high R squared, it's not necessarily a good model. And in fact, the linear trend line that we saw before, let me back up a little bit. You see how that has an R squared of 0.95? But it's the wrong model, right? So this is kind of why I didn't really mention it. It's not necessarily a good measure, and it really shouldn't be the only thing you depend on to let you know whether a trend model is valid. We really need to make sure that the assumptions have been satisfied so that we can trust the analysis method. Okay, so back to the good model again. So that looks pretty good. Let's do the residual analysis on it, which I've already conveniently done. Do the residuals have a mean of 0? Well, let's place the average line on the residuals again. And yep, they sure do. Do the residuals appear unrelated to the independent variable? For the most part, yeah. I mean, there's a little bit of grouping up, down, near 0. But for the most part, they look really good. With real data, it's very unlikely that you'll get residuals that look exactly perfect. This is probably the best you're going to get. So we'll say, yes, we can trust our model estimates. Should we add the confidence bands? Well, are the residuals unlikely to be correlated with one another? Is the variation between windmills likely to be related? These windmills, all different places, it's very unlikely that the variation between windmills is related. Does the spread of the residuals look roughly the same with changes in the independent variable? This one's a little different than the last one in that we actually have the spread does change here and looks like it dips in a little bit right here. But again, with real data, it's not going to look perfect all the time. These are an example of residuals for a model that has been correctly specified and for which all the assumptions are valid, or are hold. Okay, so we can go ahead and add the confidence bands to this, edit the trend line, and then check show confidence bands. Cool. So there are actually more than 4 model types in Tableau. If you notice, when I went to edit the trend line, we have this little spinner in the middle that lets us change the polynomial degree. So degree 3 actually does fit this data really well, but what happens if I crank it all the way up to 8? That's the maximum allowable for now. Does this look like it fits the data really well? See some nods. Yeah, it looks like it fits the data like, impossibly well, in fact. But is this a good model? To answer that question, let me zoom out a little bit. According to this model, when wind speed gets to about 17 meters per second, the power output drops off. And then the moment it goes past 18 meters per second, power output for the windmills goes blasting off. So that's what the model is telling us, which is a little strange, because does it look like the data suggests that? For the most part, no. These 3 points here maybe, but the rest of it don't suggest that at all. Now this is an example of a model that has been overfit. We chose a model that is more complex than we have justification for. And this is why choosing linear if you don't know is a really good first guess, because it's the simplest model that we have. So when choosing a trend model, only choose a complex model when you have justification for doing so. And our justification, either we can try to find one by checking the residuals, but also if you look up windmills on Wikipedia, you can see that power output is related in a cubic way to wind speed. Any questions? Huh?
So to solve the problem of overfitting, can you split the data into 2 sets and make them like piecewise combined models?
Okay. I see. Yeah, so the question was, to help solve the problem of overfitting, can we split the model into 2 different data sets? I don't think that will necessarily solve the problem of overfitting. So overfitting happens when you make the model more complex than it really should be. So it doesn't really matter how you partition the data, it'll still happen. So even if I cut off these 3 points right here and fit an 8th degree polynomial to it, it wouldn't make it a good model because we don't really have justification for that many terms in a polynomial. Or that many terms of the model, if that makes sense. Yeah. 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 Oh, good question. So the question was, if I were to say, cut the data in half and then fit a model to each half of it. So that's actually a different kind of model. I can't remember the word for it, but that's beyond the scope of the session and beyond the capabilities of Tableau's built-in stuff. Yeah. But come see me at the end, and I can talk to you about how you might go about doing something like that. Slides. To review, in order for our ordinary least squares estimates, that's the line that we fit, and their confidence bands to be valid, we need to answer yes to a series of questions. The first 2 questions are required for the model estimates to make sense, and the second 2 are required for the confidence bands to make sense. I won't read them off for you guys again. Trend lines are good at answering questions like, what is the relationship between profit and CEO compensation? Or, when wind speed changes, how does windmill power output change? Or, does compensation change in a meaningful way as age changes? So we saw with trend lines that if the data are autocorrelated, as in if the variance between data points are related to each other data point, we can't really trust our confidence bands, and so we really can't say very much about data that we don't have. This happens often with time series data. How many people have a date and a measure together in a data source? Yep, pretty much everybody. So you have a time series. And typically with the time series, the values are autocorrelated, as in the future depends on the past. So for that, trend lines is not very good, but we have forecasting. For example, you may want to know, given data on past visits, how many times will All I Want for Christmas Is You be played in December of 2016? So this is old data. YouTube recently changed its policy, and I guess Mariah Carey no longer wishes to show statistics for her video. But we can still analyze the old data. So let's take a look. So here's the data. I pulled it right off of YouTube. Let's place the total number of views on rows. That's the total number of times that All I Want for Christmas Is You has been played, that we have data for. Then I'm going to drag out date. And remember, I want to know how many times it'll be played on December of 2016. So let's take this down to the month level. OK, so it's very similar to the image that I had before. From the analytics pane, I'm going to choose forecast, drag it out, and boom. Tableau gave me a forecast. We didn't have to choose a model. We just got a forecast. Tableau's forecasting uses a method called exponential smoothing. Exponential smoothing assumes that data points in the recent past are more predictive of the future than data points in the distant past. When you initiate a forecast, we will compute 8 different exponential smoothing models and then pick the best one based on AIC. AIC is a relative quality metric, and it stands for Aka-Ike Information Criterion. So it's a relative quality metric. It only tells us which is the best model of the 8 that we have. But I'd like to know, is this a quality forecast? How reliable is my estimate that All I Want for Christmas Is You will be played 49 million times in December of last year? So we need to learn a little bit more about what it means for a forecasting model to be of good quality. For our purposes, we will consider only one quality metric, and that is the mean absolute scaled error, or the maze. The maze compares the error of your model with the error of the naive forecast, which we'll talk about on the next slide. Maze is typically between 0, which is impossibly good, and 1, which is bad. Maze can actually be greater than 1, and that's just really bad. The naive forecast. The naive forecast is just the forecast that copies values from the last observed value. In the case of a seasonal forecast, we would just be copying values from the last observed season. So how reliable is my estimate? Well, I'm going to right-click on the viz. Under the forecast submenu, I'll choose Describe Forecast. We can see that the quality is OK. And the maze is actually hiding in the Models tab. So let me zoom in on that, right here. And it's right there in the middle, 0.41. This model has 41% as much error as the naive forecast, which is OK. This blue shaded region are the prediction intervals. These are very similar in concept to the confidence bands, in that they give you a range in which the true model is likely to lie. For just an OK forecast, we're not really sure what the future is going to be, so we end up having to cast a pretty wide net. Questions so far? How many people have used forecasting to answer a question? Oh, good. Lots of you. Great. So in the course of using forecasting, you may have encountered a forecast that you didn't expect. Sometimes the forecast that you don't expect is of poor quality. Let's look at a couple of scenarios when we get a forecast that is poor quality and that we didn't expect, and what we can do about them. So I, like you, have amassed a number of t-shirts over the years. I moved recently, and my wife found my boxes of t-shirts sitting in the closet and said, Tyler, you really should get rid of those. I said, no, sweetie, I'm wearing them out pretty steadily. The number of t-shirts I have is declining over time. We don't need to do anything about that. Well, my wife works at Tableau too, so she took my data. Oh, of course, I've been keeping t-shirt inventory data since I was in college. So she took my data, placed number of t-shirts on rows, date, on columns at the quarter level, and then she went to the analytics pane, drug out a forecast, and boom. The number of t-shirts I have looks to remain constant for the foreseeable future. Now, this is not a forecast that I would expect, but is it a quality forecast? Well, right-click on the viz, describe forecast, and we'll find the maze here, and we can see that the maze is 1.4. This model has 140% as much error as the naive forecast. We would have been better off just copying values forward. Luckily, for me, I think that I can do better. The reason I think that is because I am noticing what is known as a structural break in the data. The process that was generating my data before, say for example when I was in college, is different than the process that is generating my data now that I work at Tableau. So again, here are my formative years, not really getting a whole lot of t-shirts. This is right around the time I started working at Tableau, so we got t-shirts for like every recruiting event, every release, what have you. So exponential smoothing, remember, assumes that the recent past is more predictive of the future than the distant past. So if you notice a structural break in your data, you can choose to filter the points out preceding the break to see if that gets you a better forecast. Now, I cannot filter on a measure when forecasting is active. That's just a quirk of Tableau, but I can filter on a date. So I'm going to right-click on my date, show the filter, and then let's filter out that data from my formative years in college, right up to about, let's say, there. Oh, too far. There. Okay, so you see how my forecast changed? But is this a quality forecast? Let's take a look. Describe forecast. We can see the maze is now 0.61. 61% as much error as the naive forecast, which is better, but still only okay. Well, I think we can do better still, because I'm noticing yet another structural break here, right around here. This is right around the time that Tableau decided that giving us t-shirts for every little thing probably is not a good long-term strategy, at least for everyone's t-shirt collection. So instead, now we get little patches for every release that take up a lot less space. Okay, so let's filter out the points preceding the break there. I think right up to about, too far, right there. The forecast didn't change much, but the prediction intervals actually got a little bit narrower. Is this a quality forecast? Well, let's describe the forecast again. And we can see the maze is down to 0.46. 46% as much error as the naive forecast, which is certainly much better than where we started. So I guess I get to keep all my t-shirts after all, because yeah, it certainly looks like they're declining steadily over time. So behind the boxes of t-shirts, my wife found my magic card collection, for which I've, of course, been keeping data on its value weekly for a few years now. So of course, they're just collecting dust. I haven't bought them out in years. My wife said, Tyler, can't you just get rid of those things too? I said, no, honey, the value is increasing over time. I should really keep these. Okay, well, working at Tableau, she of course took my data and forecasted it. And unfortunately, it looks like the value of my collection will remain constant for the foreseeable future. Is this a forecast that you would expect for this data? No, me neither. I mean, I do like my magic cards after all. Well, but let's take a look at the maze and see if this is a quality forecast. Describe forecast. And we can see that no, it really isn't. This has 99% as much error as the naive forecast. But again, I think that we can do better. The reason I think that is because notice how spiky my data is. Sometimes, if you have a lot of short-scale variation at the current date level, that might throw off your forecast. I really only care about the long-term value of my magic card collection, of course. So I can try to aggregate from week to month to try to smooth out some of that variation and maybe get a better forecast. Okay, so I'm just going to go from week to month. It smoothed out some of the variation, but it appears that my collection value is constant. Is this a quality forecast? Let's take a look. And we can see the maze is 0.87. That's better than what we had, but it still has 87% as much error as the naive forecast. Well, we're headed in the right direction, so let's try to go from month to quarter to see if that helps. Ah, that is good. But is it quality? Well, it's okay. It's certainly better than what we had. So I would conclude from this that the value of my collection is actually increasing over time, and I get to keep all my magic cards.
Using stats to lie?
Sorry?
Using stats to lie?
Using stats to lie. No, not quite. I haven't really changed the data at all, but oh yeah. Okay. Using stats to win an argument with my wife. That's the only way. I no longer have my magic cards. So, exactly. So to review, we looked at a couple of scenarios in which you get a poor quality unexpected forecast. And if you get a poor quality unexpected forecast, then ask yourself these questions. Does it look like there's a structural break in my data? Or is there a lot of short-scale variation at the current date level? Forecasting is good at answering questions like, how many visitors to my page can I expect in the future, given data on past visits? Or, based on past data, what will my inventory be in the future? Or, how is the value of my collection likely to change in the future? And there's one more left off there, and that is my wife wrong? But your mileage may vary on that. Forecasting and trend lines can be thought of as supervised machine learning algorithms. We give them a right answer, which would be our data, and then we can use the model that we create to predict data points that we don't have. Clustering is an example of an unsupervised learning algorithm. We will give it some data, but we don't really give it a right answer. So it can only really tell you about the data that you already have and not really much about data that you don't. Okay, so let's take a look at some data. My sister got me a pair of pants for my birthday this year. Same exact pair of pants that I had bought for myself the previous year, same size, same type, same brand. However, the pants I got this year were too big. The waist was too big. Now, for better or worse, I haven't lost any weight in the last year. So what happened exactly? Oftentimes, clothing manufacturers will take body measurement data, group that data into small, medium, and large categories, and then average those categories to try to figure out how big to make clothing. Because they're obviously not going to make a different pair of pants for every single person in the world. So I have here some body measurement data. Let's see if we can figure out what the average-sized small piece of clothing will look like. With the other features we've used so far, the type of viz you had was actually pretty important. With clustering, all that matters is that you have the measures that you're interested in clustering on in the viz at the level of detail you're interested in clustering. So I have here a number of different measurements. We have like arm length down to hip circumference. Let's place that on columns, or those 3 on columns. I'm going to make some small multiples here because I think it makes it easier to see the clusters, but the type of viz, again, really doesn't matter. Drag out these last 3, we'll place them on rows. And I want this at the level of detail of individual bodies. do we notice any clusters that kind of naturally arise in this data? I don't. And in general, body measurement data, people don't really tend to cluster around certain body types. They just kind of vary continuously between them all. So when I use clustering from the analytics pane, just drag out the cluster object, Tableau says that there are only 2 clusters. Tableau will try to find what is likely to be the number of clusters in your data set, but if there aren't really any natural clusters that arise, it'll default to 2. I want clothing that is small, medium, or large. So instead of 2 clusters, I'm just going to choose 3. And then you can see that we reclustered it all. I'll zoom in a little bit. And this is actually why I chose the small multiples. You can kind of see where those boundaries ended up getting drawn. All right, let's answer some questions. In order to use my newly computed clusters, I need to save them to the as a group. So we'll drag the cluster object into the dimensions pane, and we'll call this sizes. And then I can use that as a category to make a text table. I'm going to place sizes on rows, measure names next to it, and then I'll place measure values on text. So notice how this is the total arm length for all the small data points. So we actually should make all these an average. So I'm going to select all the measures in the measure value shelf, and then choose average. And so we can see that in the small category, arm length is about 61 centimeters. Shoulder breadth, about 45 centimeters. Notice how Tableau didn't name this small, medium, and large for me. So clustering doesn't really care what the clusters are. It just figures out what's in them. So it's up to you to give those clusters semantic meaning. It just so happens that cluster 1 is the small one, and I made that judgment because the numbers are the smallest of all the clusters. Any questions? You guys are sharp. All right. Clustering is good at answering questions like, if I split my data into 3 groups, which data points belong to each group? Or, if I wanted to split my data into small, medium, and large categories, what is the average arm length in each category? So to recap, we talked about confidence intervals, which are good at answering questions about the population based on a sample. We talked about trend lines, which are good at answering questions about relationships between 2 measures. We talked about forecasting, which is good at answering questions about the future given data on the past. And we talked about clustering, which is good at answering questions about categories in the data. So go forth, use these features to answer a question that you have. And we have actually quite a bit of time for questions. Yeah.
2 questions.
Uh-huh.
Forecast. Can we change the exponential decay to the parameter?
Good question. So the question is, on forecasting, can we change the exponential decay parameter? So exponential smoothing models are the ones that we have are either multiplicative or additive, and then they have, we'll estimate some coefficients for them. And we don't really give you control over that. Yeah, we give you the best model based on the relative quality metric. Okay. Yeah.
The second one is on clustering.
Uh-huh.
I noticed that the shoulder arm length is at 61, 65, 67.
Mm-hmm.
So the gap change, like what determines that gap?
Oh, I see. So the way clustering works, actually I have a slide on that. You guys want to see how it works? We're going off script here. Oh, actually, did I take it out of here? Oh, I must have taken it out. OK. So sorry, I don't have the slide on this. The way clustering works is that we will choose centroids. So those are data points in the same space as your data, but not necessarily part of the data itself. And then we will run the algorithm, as in we'll step those points closer and closer so that the average distance from those points to all the points around them is at a minimum. Once the points stop moving, then we say that we're done. So that's just where the centroids ended up. Yeah. And I would say that given that data set, body measurement data tends to be normally distributed. And so you end up with a much bigger chunk in the very middle of it than you do on the edges. So the question was, I hope I repeated that. The question was, why was the difference between the clusters not uniform? And that's because the distribution of body sizes is also not uniform. It got a little bump in the near the average. So, okay, got one question here and then one over there. Mm-hmm. Oh, good question. Okay, so the question was, what is the quickest way to see the min and the max? Well, we can just, let's see, I can bring that up here. Where is it? Let's see, min and max. I don't think I can put two measure values next to each other, but you can just select all the measures and choose to aggregate as a minimum. And I think that if this is why you don't do this stuff live. I can try putting another copy of measure values on text. Oh, not quite. Okay. Come see me at the end. We can try to get both of them on the same visit once. You just want to change the aggregation. Okay. Question over there?
There's an option in the
Mm-hmm. Yeah, good question. So the question was, Tableau's trend lines allows you to include categorical factors, but can you have multiple quantitative factors factored in? And so the answer is no, unfortunately. Our ordinary least squares only gives you the relationship between one variable and one independent variable and one dependent variable. So it's definitely possible to do a multiple linear regression. It's actually pretty easy with the R integration. So if you would like to know how to do that, just shoot me an email and I can send you a workbook that has the code in it.
I got a question about the
Oh, someone using the microphone. Great, where is it? Oh, that's over there. Nice. Okay.
the forecasting.
Yeah.
Is there a way to factor in some sort of like process change? So like if your Magic cards, there was some sort of new release that increased that you expect to increase the value of Magic cards, or Mariah Carey forgets the words to a song and somehow gets popular, so her stuff gets played more, something like that.
Yeah, really good question. So again, the question was, can you factor in other factors to the forecast other than just the past data? Not natively, but that's another one that can be done using R integration. So if you shoot me an email, I can send you the code to do that. And I think that there is a demo booth in the expo hall that we're demoing R integration, and then multivariate forecast, taking into account a different categorical factor, is one of those demos. So if you head down there right now, I'm pretty sure that they'll be able to answer that question for you, or show you how it's done at least, or what it might look like. Uh-oh. Killed by the screensaver. We have a few more minutes for questions. Let me unlock this really quick.
What's the minimum number of data points you need to do a forecast?
Oh, good question. So what is the minimum number of data points you need to forecast? So we've put some hard limits in there. I can't remember off the top of my head what they all are. I think it depends on the date level that you're at. So at the year level, I think you need a minimum of 5 points. At the quarter level, I think you need a minimum of 9, or it might be 7, one of those two. But it varies depending on the date level. So because we want to estimate a seasonal forecast, and we try to determine what season you might be looking for based on the current date level, so we'll require a number of points that you have at least one season in there, if that makes sense. So like with quarter level data, we'll look for season every year, and so you need at least 4 quarters for that, and so we want to make sure to capture some data on either side, and so I think the total number that you need is 7, but I need to actually double check. I don't remember off the top of my head. So, question over there, and then one over here. Oh, yeah, absolutely. Oh, actually, well, before I do that, may I ask that you please fill out the session survey and let me know how this went. But yeah, the question was, can I put my email up? And so let me do that really quick. Yeah, feel free to shoot me questions. I'm always happy to answer. I kind of like being a teacher outside of TC sometimes too. So I had one more question over here, I think. Yeah. Oh, good question. So the question was, what does Tableau use to determine the quality of the forecast? Because there's like a quality indicator that says poor, okay, good. That's dependent only on the maze, actually. Yeah. So we have certain thresholds. I think the threshold is like 0.4 for good to okay, and then 0.7 or 0.8 from okay to bad. Yeah. Question over there?
In terms of your analytical workflow, is there a preference for when you use Tableau versus R versus other analytical tools?
Oh, that's a good question. So the question is there a preference to using Tableau over R for these kinds of analyses? So Tableau's built-in functionality, so trend lines, we only have ordinary least squares. For forecasting, we only do exponential smoothing. That isn't necessarily the best model, but it works well in most cases. So really, it's going to be dependent on what it is you want to do exactly. And if you want to use a model that Tableau doesn't offer, then you really have to go out to R and use those. But I would say that if you know that exponential smoothing, for example, would be a good forecast model for you, then use the built-in functionality in Tableau. It gives you some really nice things like the ability to click on the points and see what the values and stuff are, as well as like prediction intervals and so on. The stuff in R is a little bit harder to understand because rather than being saved off as like pills in the data source, you end up with like a whole matrix of values, and you have to kind of reference the columns and rows of that matrix to get the values out. So it's a bit more complex, but if the complexity is what you need, then you have to do what you got to do. More questions? Oh, one over there. Mm-hmm. Good question. So the question was, if I wanted to make a control chart, right, where you have an average down the middle of it and then standard deviations on either side, is there a good standard for how many standard deviations to place those lines, right? I would say that probably the most official standard would be the whole 6 sigma thing. Have you guys heard of the 6 sigma thing? That's within 6 standard deviations of the mean. For normally distributed data, that should capture 99% of values, and so anything lying outside of that would be considered an outlier. But again, it really depends on what your use case is. If you care that the values are, so the standard deviation is like the average distance from the average. And so if you have data points that really can't vary that much from the average, then you use 1 standard deviation. If you have a little bit more tolerance for it, maybe you can use 2, or 3 if you have almost no tolerance for outliers. So does that answer your question? Okay, cool. That's a good question. So the question was, when you don't have something that Tableau recognizes as a date, what can you do about forecasting it? I think your best bet is probably to use R to create the forecasts. So you can pass those values into R, massage them a little bit so that R thinks that they're dates, and then have R perform the forecast for you and give you back a result. We have, again, at the demo booth downstairs, there's a pretty good example of using it didn't have like non-date fields in it, but you can imagine how you might extend it to use non-date fields pretty simply. The code will be roughly the same. Yeah. More questions? I think that was it. Oh, wait, one more. Yeah. Good question. So the question was, does Tableau have any plans to integrate logit or probit models natively in the software? I generally can't talk about the things that we have planned, but we don't have those things natively. You'll need to call out to R to use them. Yeah, that's all I can really say. So, yes. Well, if there are no more questions, thank you all so much for coming. Again, please fill out the session survey form. I've been doing this for like 5 years now, and this is drastically different than it was even like 5 years ago, based on the feedback that I've received. So please let me know what you thought. Thank you all for coming.